Alright, so this will be the complex analysis polar form part 2. In the previous video, I talked about how to convert from Cartesian coordinates into polar coordinates and a little bit about how useful the polar form is in complex analysis. In this video, I'll be talking about how to convert it the other way around, how to get from polar back to Cartesian, and some important properties of angles that I need to go over now. So basically, if let's say we have a complex number written in the polar form 3ei pi over 4, and we want to convert it back to Cartesian, our formulas we're going to use are x equals r cosine theta, y equals r sine theta. Kind of like, kind of familiar stuff. So all we're really going to do is x is going to be equal to 3 times the cosine of pi over 4. And that is equal to root 2 over 3 times root 2 over 2. So our x is 3 times root 2 over 2. And our y is going to be just simply 3 sine of pi over 4. And that's just going to be equal to 3 square root of 2 over 2. And there you have it. So really we can write this as 3 square root 2 over 2 plus 3 square root 2 over 2i. That's how we would represent this number in Cartesian form. And of course you can check this by simply just using the formula from the last video. Just do x squared plus y squared, and then use theta is equal to r tangent of y over x. So just kind of use the formula from the last video to kind of go backwards and check yourself. Now, another important property of polar form is that when you have an angle like pi over 4, if you add 2 pi to that, not just 2 pi, any multiple of 2 pi to that angle, you're going to get the exact same result. So what does that mean? That means that 3e to the I pi over 4 is exactly the same thing as 3e to the 9 pi over 4. And it can also be the same thing as plus 17 pi over 4. And here's the kind of illustration of that. So let's say we have our pi over 4s right here. That's our pi over 4. And we go around the unit circle, because this is a unit circle. So we go all the way around the unit circle. And if we go around 2 pi, that's the full length of the unit circle, really any circle. Then you're going to get back the exact same angle. So really pi over 4 is the same thing as 9 pi over 4. And we can go around this indefinitely. We can go any 2n pi times. So that's an important thing to note. And I'll be talking, there's more to this than that. There's some other properties, and I'll be talking about them in later videos. But this is important to kind of get an idea of what's going on here now. So really, theta, which is equal to the argument of z, which I talked in the last video, can also be written as the argument of z plus 2n pi, such that n is an integer. This is important that n is an integer, because if n is not an integer, this form is not accurate. And that kind of makes intuitive sense, because if you kind of go here, and you kind of, you only go around, let's just say to here maybe, and that's, let's just say you kind of go something like, pi over, I guess pi over like e distance, or something like that. Something, something not integer based, something that's not an integer. That clearly would not be equal to this angle, and go ahead and just erase that. Basically, the whole idea is it has to be an integer multiple of 2 pi in order for this result to be true, and that is going to be very useful in later videos. This is kind of just kind of getting an idea of what's going on, because of course this is kind of the first set of videos. This is going to get a lot more complicated later on. So anyway, this is kind of polar form. In the next video, I'll be talking about de Moivre's theorem and why that's so useful, and that's probably going to be one of the most useful results. It probably is one of the most useful results in complex analysis, period, aside from maybe Cauchy's integral formula, which comes much, much later. Anyway, so that's all for this video, and I will see you guys in the next one.